In this video, we'll be looking at linear approximation. So remember that the equation of a tangent line is mx minus x1 plus y1. That'll give you a y equals equation that's going to be tangent to a curve. A tangent line requires an x value, which we're given here of 1. It also requires a y value, which we can find by plugging in for x. So plug in x into our given function, and right away we can get the y value. 1 raised to any power is 1, so negative 5/3 just becomes 1, and 2 times 1 is 2. So we get a y value of 2 without too much work there. So we have our x1 given, our y1 all but given. We need our slope, or m. That's the third ingredient for a tangent line. And a slope can be found by taking the derivative. So a simple application of the power rule, bringing down the negative 5/3 and then decrementing the negative 5/3 by 1 should give us negative 8/3 for our exponent. So this is the derivative, the slope at any point. We want the slope at the point of tangency, which is at x equals 1. So plugging 1 in will give us this expression, and likewise that'll give us negative 10/3 for our slope. So our tangent line equation is now complete. It's negative, get the software to cooperate, negative 10/3 x minus, try to color code this, x minus 1 plus 2. Okay, so this line will approximate the function we're given at points very close to 1. And the point of interest is quite close to 1, 0.85. So plugging 0.85 into the given function is hard, but plugging it into the linear equation that we created, well, that's relatively easy. So replace x with the point of interest, 0.85. 0.85 take away 1. Let's see, that should be negative 0.15, 15 hundredths. And plus 2, sorry. So if we can do this without a calculator, that'll be really impressive. So negative 15 over 100 is another way to write that decimal as a fraction. It's a little bit easier to calculate with. Plus 2. So the two negatives will cancel, and we have some fraction simplification here. And I suppose you could use a calculator in a pinch, but why bother? You have a negative times negative, and it'll give you a positive 5 over 10 plus 2, better known as 2.5. So our approximation is 2.5. Okay. Now, some of the harder work, especially without a graph, can be in determining whether or not this is an over or under approximation. Yes, it's close to 2. Well, that's expected because 0.85 is close to 1. So how do we determine the actual nature of the approximation, if it's an under or an over approximation? I think some of my work here will be underneath the... All right, bear with me on this software. It's sort of new. So we're considering x equaling 0.85. So that's when x is greater than 0. I wrote greater than 1 there, but actually greater than 0 is what I meant to. So when x is positive, which is what we're considering, because x is 1, the second derivative, which will tell us about concavity, well, we can find the second derivative by simply taking the derivative of the derivative. So the little red star there indicates that I'm just pulling that information down, and I'm now doing the power rule again upon it to create the second derivative. So this will tell me the nature of the curve's concavity at any point. And again, the point of interest is when x equals 1. So simply plug 1 into your second derivative. The fact we're plugging in 1 makes much of this calculation, despite looking ugly, being relatively easy, because 1 raised to any power is just 1. So we get 80 over 9. Sort of a funky number, but the point is that it's positive. And because this number is positive, our second derivative being positive implies that our original function is concave up. Now, when a function is concave up, you have this sort of smiley face action here, and you'll observe that the tangent line, the lines tangent to a concave up function, all lie below the curve. All those blue lines are below the concave up curve. And thus, because our approximations are linear on a concave up behavior, our approximations are going to be an under approximation, because we're literally below the function. because the function is bending away from the line at every point of tangency. So to finish up our answer, our second derivative was positive, therefore our graph is concave up. Because our graph is concave up, as you can see from this picture here, we must have come up with an under approximation for the actual answer. Hope this helps.